The rectangle signal serves two significant roles in signal processing. First, when multiplied by another signal, the rectangle acts as a window that isolates a specific region of a signal. Second, when several rectangle functions are scaled, shifted, and summed, they can be conveniently used as building blocks to approximate more complicated signals. In this short lecture, we'll overview the mathematical definition of the rectangle function, and we'll illustrate its use as both a window function and as a basis for approximating more complicated signals. The rectangle function is a simple but important signal with significant applications throughout the field of signal processing. It's a simple signal to sketch or plot, and it's a simple signal to define mathematically. We define the rectangle function like this. For all times that are less than -1/2, the rectangle function or signal is equal to 0. For times that are in the interval between -1/2 and 1/2, the rectangle signal takes a value of 1. And for all times that are greater than 1/2, the rectangle signal takes a value of 0 again. Now, at the two discontinuities, when time is equal to -1/2, this region, and when time is equal to 1/2, which is this region, there's a little bit of inconsistency in the way people assign values to the rectangle signal. Some people will assign a value of 0 to the rectangle there. Some people will assign a value of 1. And some people will assign a value of 1/2. And they'll do the same thing in both of those discontinuities. Zero would be assigning it the value that it takes outside of its center interval. If you give it a value of 1, we're assigning it the value it takes at the inside of that interval. And if you assign it a value of 1/2, that would be setting it equal to the average. All of those are done, but most of the time it won't matter what we define the signal to be at those discontinuities. Now let's see how the rectangle function is used as a window to isolate a specific region of a signal. Suppose we're only interested in the region of this signal between plus and minus 1/2 seconds. So only the region from -1/2 to 1/2. So everything outside of that region we don't care about, and everything inside that region we do. So one way to get rid of this stuff would be to multiply it by 0, likewise outside of that region, and in the interval that we're interested in, we can multiply it by 1. Well, that would be the same as multiplying by a rectangle function that turns on at -1/2 and then turns off again at 1/2, which is the standard definition for the rectangle function. So if we multiply this signal by a rectangle, we would see something like this. So outside of the interval, all values of the signal would be 0, but inside the interval, the signal would retain its original values. Well, this is commonly done when we want to analyze the signal only over some limited region, and we want to process the signal without processing the values outside of the interval. If we want to analyze a region of the signal that is not centered at 0 and has a width different than 1, which are the parameters we associate with the standard window, then we need to, with the standard rectangle window, then we need to scale and shift the rectangle signal. Well, here's the equation for a scaled and shifted rectangle signal. If we look at this signal in time, it's a rectangle whose height or amplitude is equal to A. Its center is at the time t0, and its width about that center is equal to delta. So this point here is t0 plus delta over 2, and this point is t0 minus delta over 2. If we look at a specific example, this is a scaled and shifted rectangle function. It's been shifted to a time t0 equal to 0.4 seconds. It has a width associated with it of 0.2 seconds, and it has an amplitude equal to -4. So once we think about a scaled and shifted rectangle, we can now talk about building more complicated signals by combining several scaled and shifted rectangle signals. Well, here's the superposition equation for creating a complicated signal from rectangles. Our signal S of t is the summation, as k goes from -infinity to infinity, of an amplitude a sub k times a rectangle that has a width of delta and has been shifted to k times delta. So if we take a look at this, what a segment of this signal might look like in time. So when k is equal to 0, our rectangle is going to be centered at 0. It's going to have some height a0. So this value would be a0, and it'll extend to delta over 2 in that direction and negative delta over 2 in this direction. And then out here at delta, we're going to have another one, and it's going to have some height a1, and it'll extend out to 3 delta over 2. And that kind of thing will keep happening out that direction. And then back in this direction, we might have at negative delta, we might actually have something that has a negative amplitude associated with it. And if we look at this overall signal then, and we add all of these up, over this region anyway, it'll look something like this. We'll just trace it along, and then whatever happens beyond that. So there's an example of another signal. In this case, this location here, so this is t equals 0. The halfway point here must be delta. Halfway here, 2 delta. Halfway here, 3 delta, and so forth. And over here, this might be negative delta, negative 2 delta, negative 3 delta, and so forth. This value here, a0, looking on this axis, that's equal to 4. a1 appears to be equal to roughly 3. a2 is equal to 0. a3, that's roughly negative 3. and so forth. Likewise, this happens to be symmetric. At -1, we got a value of 3. A -2 is equal to 0, and a -3 looks like it's equal to -3. And then if we look at this width here, that's delta. Well, there, it doesn't look like an interesting signal. It still looks more like a staircase than some kind of interesting signal that we might see, but we can make the signal start to look a little bit more interesting if we reduce delta. So let me show you an example here. In this case, what we've made, we've made delta equal to 1/16 of a second. And now you might recognize this signal, but it turns out that we've made our coefficients equal to 4 times the cosine of 2 pi times k delta over 2. And by doing that with k, and that's actually very similar to the coefficients we had for the previous picture, but our delta was a little bit larger. And you can start to see that this looks like a cosine, but it still exhibits some of the staircase effect. Now, in this case, we've made delta equal 1/64 of a second. And once again, AK is 4 times the cosine of 2 pi k times delta over 2. And in that case, we're starting to eliminate much of the effects of the staircase, and we're approximating a sine wave, in this case a cosine, as a summation of many of these rectangle functions. So the rectangle is a very simple signal, but through scaling, shifting, and superposition, we can use it as an apodizing window for signal analysis and as a building block for approximating more complicated signals. So there you have it. That's the rectangle signal.